So good afternoon to all. I welcome you all to this 12th session of this FDP, and this session will be on tools and techniques of quantum computing, and that will be delivered by Dr. Gunajit Kalita. So I request Dr. Kalita to start the session.
Thank you, Master. So, last class we discussed about Haskell and few topics regarding Haskell left. So, I first finish that and then we'll try to see two tools. Try to write few small programs, how we can handle or use these tools. But before that, let me finish the last class of the course and I left. So, I left it from here. Function composition in Haskell. So it's basically process of using output of one function as input to the other, like that. So normally this type of things are here in maths, and many times we normally face this type of thing. So you see that f is a function and its input is another function gx. So that type of things once we want to implement, particularly when you go for implementation of circuit and gates, this type of functions are important or required. So moving, anyway, if I make it big, then it become problem. Anyway, so here one example. Say we have a function here, even number. So here it will take an integer and return one boolean, true or false. Take an integer. And next is another function. We just here prototype is declared here. N02, right? And it will take boolean and return a string. Now, in the definition of the function, because this way we normally define the function in Haskell, also in Kuiper, also many languages, many quantum related languages. Anyway, so now we define that even number function. Name is EV, any name. You can put any name here. You can write any name if you want. Suppose this is just a function name, F. So you can write it, no problem. Up to you. So, okay. So what we'll do, we'll check whether that is even or not. So for that, we do what? If RAM is basically an operator to find the remainder. So if you divide this by 2 and get 0, which is equal, then it's an even number. So then it will become true. If you see the prototype of the function, f even number will take an integer and return one boolean. So here also, it will checking one integer and returning a boolean, that is true. Okay. If it is divisible by 0, then true, otherwise false. So that is the simple function definition over here. Similar way, NO2, which is another function. So here if you see, it will take one boolean and it will return a string. So now if you see x, if it is true, then it will tell that this is an even number. Otherwise, it will tell it is odd number. But if you return a string, this is basically string. Then this means it will return this string or else part of the string, whatever, depending on the condition. Now, if we write the main function, let me make it a little big. So what I can do, Okay, so I'm writing the main function now here. This is my main function. Okay, so this main function, if you see, we are calling this suppose these two functions together. Meaning is NO2, that is our function for already we have defined that, and F even, that also another function we define. These two. So what will happen? First, F even number will calculate work on printing, and this will return a boolean. So now NO2 will take that boolean and return a string. All right. So now since 20 is the number, so definitely it is return true. And if you see the function NO2, if that x which is true now, then this is an even number. So that will appear. If we change it, it will be otherwise. So this is basically the function composition in ASCII. So, this type of syntax or utility are very important in case of designing circuit. Another term is modules. So normally different classes are there for that. It is similar to the module, similar like the modules you find in other languages like Java or C++. Anyway, so the list we know already, we understand the list. So here if you see, the from this will, because we are supposed to use some sort of again function that we want to implement. So for that actually we need to import data and the list component out of that. Now suppose we are writing some string over there. This is just a message. Next one is suppose interparse. So if we write interparse, Google dot say where will we interparse this? We are putting here a dot. If you can see, just wait. That is my pen. So interparse at a particular point. So what is that? That is dot. So if I see google.com, so there we need to interparse. So if you want to interparse there, the Google and com will be separated. So sometimes we require that type of operations. Similarly, another is these are all part of the data class, so data package or module, whatever you want to say. Next is intercalate. Intercalate, you see some this particular list is there. Let's start with Haskell. Right? So intercalate basically do what it will change it. Just wait. Let me make my pen correct. So, so it will come as let's start with Haskell. They are separate entities, so it will be intercalate or intercalated or combined like that. Next, print split at particular. Suppose digit I'm writing 5. So it will be GUE CE AEC. This is my string. That 5 it will be splitted 1, 2, 3, 4, 5. So this will be get separated. Right, so this can be done. Similarly, you can use sort. All right, that particular list is integer list is given, so it will be sorted depending on the weight. Okay, so these are part of your data.list package that you can use if you want. So sometimes we require this type of thing also. Next is your character module or CHR module. So some predefined character functions are available like. Well, of course, these are not that much important for a circuit purpose, but maybe if you want to label some circuit, then they may be important. So again, here part of data, so you need to call that switch here. So similar way to upper is a function. We change this to capital B. Now words, how many words are there? That will be returned. Lower will be returned to B, and how many words, like that. So given this, you have to use CH harmony. Next one is your math module. This is important because in keeper, it's having a big role. So it's very important. Normally, unsorted value added here. One example is this. So when you want to utilize this, you have to give this data application. Okay. Now, normally what import qualified data but map as map, right? This is important if you use GHCI compiler. So if you use this compiler, this is required, otherwise it is not required. So why what we are doing, say it will take one list. If you see that the integer is there, it will take one list of integer and it will map to that. So I'm creating one, we can think this to be a function or not actually a function, this sort of class you can say. So that we are doing. Next, we'll try to create one, if you see here, it is a list basically. So again, making some pair out of that. So for that purpose, make a pair we are using, right? So we are basically relating to that. Now question is how we are doing this. Because we want to make something like this. We have a list of list 1, 2, suppose this. We want to make a pair like this 1, and it is suppose like 2. So we have seen that function composition, this type of things are required. So if you want to do that type of operation or want something like this, then you can use this. So where make pair will be of this type. So meaning whatever index you given, that will be one data. So if you print, so your output will be like this. Right? Here your n value is given as 5. You change it and you can do whatever you want. So basically, when you require some function to work like this way, all right. So then you use this concept. Again, it depends on you whether you want to use or not. Another is your set module. Set module is basically what? Again, it is part of data. So we are taking two variables, x1 and x2. Next, what we are doing, we are creating a set. Here, set is not like that. Suppose AEC, and they are text processing purpose, not very important for scientific purpose. ACCSE, if you create a set normally, common will remove. It should be AECS, but it is not like that in this case. In this case, what will happen? First, we will take the first word, okay, or you can say, what to say, in ordered form, you can consider C. AC is done. Next, you see, next letter will be again small c because it is in order. So A, capital C, then small c. You can say it descending order. Capital A, capital C, then small c. Right? It will be there. Next E is there. When it will try to see E, it is already there. Then it will remove. And then this is already done. Next S is left. S will be there. So here actually we are creating set kind of. If you see this one, again Gauhati University EC, where C will come first because it is in terms of positional thing, it will be the first one. So C will come first, then E, so one C will be there, okay? And then Z and like that way. So again another set will be created. But when you want to utilize this, output is normally this will come like this from list. This also will be part of that. This is our actual output, but this particular word also will come. If you use print particularly, okay. But if you use this set 1 or set 2, then of course this will not on means computation purpose we will use set 1 and set 2. But if once you use them with print, that form list will appear. That we just can't help, it will be there. Another is custom module, meaning you can create your own module. Suppose module custom. Module is the reserve word you have to write. Custom is basically one name you can put over here. So like show event and show boolean. Suppose your name, user defined, these are user defined. These are user defined. So next, what in show event, it will take an integer, return a boolean. So suppose we are supposed to define this function. Show event x, that will take an integer do. What if it is a remainder of that is 0, it will return true and the rest false. So show event function is like this. Next, say show boolean, it will take boolean one input and return one integer. So we'll define the function. This is function definition. Function definition is this. What if c is true, whatever is given, then it will return 1, it will return an integer, otherwise 0. So now question is, since this custom or user defined module, so this must be named as some name. Suppose username say xy dot xs, xs for Haskell. Right, username you have to write. Next, we'll do what? We'll import the custom. All right, import that custom. The name is actually the xy, so we have to write that. Name is xy, import xy. Anyway, and then main do print show event 6, right? Because this function take one integer, return a boolean, and show boolean is a function which will take one boolean and return an integer. And now this file must have a name, say maybe main.xs or some name. So this is the function to execute, right? So this will, as per this definition of the function, whatever you have defined here, it will work. First one will return the boolean, second one will return one number, right? So if it is 6 is 2, it will be 2, and this will return one what? This is 1, so it will return 1. Right? Output will be for this function directly. So this way you can use your own module, custom module. And next is your functor. It is basically some of them already we have used. Functor in Haskell kind of functional representation. The different types can be mapped over. Basically, it's in the class. And for implement polymorphism, functions are used. So we have used tuple, list. Also, recently have seen map. These are basically instance of this functor classes. And basically, LIST. These are part of data again. Anyway, for example, let us say class. These are your reserve word. So our the functor is your f. Right? This is also reserved functor. So our name is f. Now we are mapping that f with the name f maps. Right. So a maybe whatever value is given, and b will be that value. Okay, and this will return a functor. Again, the first value whatever is there, that will again return functor and b. It means another value. So in main, you suppose we'll use map is reserved or inbuilt function. So it will do what? Map subtract 2, and it will be a list. Right? So subtract is a function. So what this will do, we have seen that subtract. So subtract is a function. What will do? From this list, it will subtract. From each element of this list, it will subtract 2. Means output of this will be 0, 2, 4, and 6. Right? Now this is a map inbuilt. Now this f map is what? It is a functor you have defined this way. Right? So what will do here? Same thing, subtract. So again, result will be also same. The first one is basically that map is inbuilt, and that this f map you have defined over here. Both are working similar way. So what is the difference? There is a difference. Right? Map is inbuilt, f map you have defined. You see here. So that is your prototype. There is a difference. What is the difference? Say if now we want to print using that f map functor, print f map plus 5 just 20. So your output will be like this, just 25. Next, print f map plus nothing. Then your output will be nothing, because nothing is given there. Nothing is a message, but no numbers are given. So this cannot be done in math. So you can use this sort of things using your own function. So these are something, if you want some interactive program, these are required. So when you use this. Next is your monoid. Monoid and monad, two things are there in Haskell. So they are also very important. These are basically some functions actually, and operation. I mean, function will actually perform operation. So function and operator basically. So output always depend on that. Suppose say one function is there, star, that is multiplication. Multiplication function is there. Another function is there, so that will suppose some sort of integer. Now, whatever the input, output may be same always. Just for example, so that is if we multiply a number, suppose it is a multiplication, and number is suppose 1, that we expect. Suppose a into 1 will be a, then it is possible. All right. Okay, so that is if multiply a number by 1, you will get the same number. All right, you will get the same number. This is example. You can make it a into 2, so it will be at whatever 2 of a will be there. That is also okay. So this is a different, I mean, requirement. But this is another requirement. So monoid basically made for that. So one example you will see, same type monoid. The monoid class, you see, we name the monoid as M here. M is the monoid, where we will create lots of them. So one is M empty. M empty is monoid, or defined as emptiness. M append, or appending. How we'll do that? You see how you can do. Two monoid will be appended, and resultant will be also a monoid. That's why it is 3M you have seen. The M concat, meaning is with the existing list, monoid will be joined. Another form of that, M concat, a folder, M append, and M empty. Meaning is there is already existing, I mean, list with M append is used. So meaning is your new monoid will be joined, and last one will be simply empty. Okay. For example, you see here, there is a function say multi. It will take one integer, return one integer. So this definition is like this: x into 1. It may be x into 2, x into 3, whatever you want. So simple function. Another is suppose add. Add is another. So here it will take an integer and return an integer. Similar. What is x? X is x plus 0. So this is our function definition. This is one function, another function. Now we'll test it. Print that function we have called over here multi 20. So since you multiply 20, so result will be 20. If you add 15, result will be 15. All right. So if sometime you require some sort of format like this, so maybe you can use. Again, these are directly not used in circuit for language purpose there. Another important pointer type of concept is there in Haskell, that is known as zipper. So zipper can be used particularly some specific location of data. If you want to see like three kind of things here, then. So this is a small example of that. Say data is a list is basically that. So we have created one list A, right? So here these are show, read, equal, odd. All these things we have seen. What is odd? What is equality concept? Read. So all these we have seen. All right. Earlier classes we have seen all this. So here we are do what? Initially it is empty, and then when you want to construct it list, it may derive show or read or equal, that is equality testing, and odd, this part. So those who have remembered these things, maybe I mean you can recollect that. Now our zipper will be what? We are creating, you see, if you write something like this, it is basically index sort of things. Index. So out of a list, in this case it may be a tree structure, you can assume. So where it located, that we want to see. So these are indexing means the location. Now here we have defined two functor kind of things. So go forward and go back. So go forward what? We're using a zipper. So list A. So it will be again another zipper, which is it will take a list which is a zipper. It will again return a list which is a zipper. So basically pointing to some location. Zipper list means basically pointing to location. Go forward case, what will happen? Say if we define something like this, say x, axis and bs, suppose. Alright, go forward meaning is axis will come before. So axis will come before here, right? And x will take the position, so x colon bs, if you see that. Required means the reverse. So again go back, required list, again this definition will be same, backward or forward. Only how you implement will be different. So go back, if you see axis b bs. So what b will now it is backward, so if you see b will come here, right? So it is coming backward. So like this coming forward, so here it is backward. That is the definition. We will run this using a main function. So we are creating a list 1, 2, 3, 4, name is list ex. So if we call the function go forward and list ex, right? And you see we have given an empty sort of things initially, because this empty is defined over here. Then go back 4, first one is 4 and next is 3, 2, 1. Basically this form basically, sorry, which one? This form. So now what will happen? Due to the forward, it will be like this. 1 will go back and 2, 3, 4 will, that's why remain. So it's like this. And for the backward purpose, if you see, it will happen this way. So 2, 1 will be there, right? And 4 will go back to 3. I mean 3 actually basically will come here. So it will create one sublist or substring. So this is 3, 4. So basically we will create some tuple at the end. They are list, but at the end they will create some tuple. So changing of position or pointing the position can be done using zipper. So this is basically a brief way about Haskell. So those interested can look into the materials available in net and you can see. So once you get idea using Haskell, then it will be easier for you to go to Kuiper. So initially it will be difficult to imbibe the Kuiper, because a little bit not that was very conventional kind of thing. Few of them are yes, but similar to that Haskell, and few of them are not. Most of the map we have studied here and functor we have studied there. These are like that. This type of things will be available there in Kuiper. So you try, read lots of manuals are there, examples also there. You read and try if you are interested. Um, this is all about your um, Haskell. Next, we'll try to see two tools today. Uh, first one, okay, before that, let me see something left. Okay, let me just see this and we'll try to use this because first we'll use this one, CIRQ. So this we'll use. So here, yesterday I told you I forgot to say what is a moment. So if this is a quantum circuit or reversible circuit, then um, we say these are our qubit, means basically the lines we say. These are our qubit. Alright, and we're applying some gates over here. Now, there was some sort of block. So here is the single qubit gates are used. So this will be a 2 qubit gate. If you see the second one, 2 qubit gate. Another 2 qubit gates are there. So it may happen this 2 qubit gate will form a block, or another 2 qubit gate is there. This will form a block. All three of circuit is a moment, right? And gate are basically the operations. So that is the thing. Gates are operation. These are basically the operations. So in a particular moment, what happened? What is the state of the circuit? Like that, the input and the change, that is the output. Yes, yes. So that is a moment. So these we need to again do what implement in case of doing this. So in CRQ, we first see what is that. Already we have discussed. So the circuit class is the primary representative of quantum programs in CRQ, and a circuit is basically a collection of moments. In those sort of blocks. The moment is a collection of operation, again, because gate is basically an operation. So ultimately those block will be number of gates together. So ultimately that all act during the same step time scale, and same moment. Meaning this at this moment, at this time, all the gates are working. That is it. Anyway, so operation is some effect. So that is basically when you use the gate on the qubit, so that is the gate operation. So it's having an effect. So it will create a moment ultimately. So what we'll do, suppose if we install a CRQ from Google, all right. So small example is there. All right. We need to do similar like Python kind of thing because we'll implement this in any Python framework or supporting editor like that. Say import CRQ, so that we know this you have to write. Another terminology also sometimes is required. Import CRQ Google. So this is also important. Sometimes we need to write import CIRQ Google. This is also important because many update things are there available in this package. So what we are doing, we are creating qubits, like grid kind of qubit, whatever xy value is given, and what is that? How this xy value is given? This value is given in this way. For x in range 3, for y in range 3. So basically, we are creating a qubit of 3 into 3, I mean 0 to 3, so ultimately that numbers. Now for the first qubit you can print this, you print qubit 0. Alright. So this way you can create one circuit. So notion of gate is basically again you have to use that. There suppose not gate or Pauli gate is X. Pauli X gate basically that is a not flipping for flipping bit flipping purpose. There will be Hadmard gate H. Alright. Like that way, lots of gates are there. C not gate is there. Alright. In fact, I think there is not, CNOT gate is there. A control Z gate is there, lots of gates. The Pauli gate, suppose this particular function if you want to see. So for this, let me stop here, we'll try to see that tool. What I need to do, from here. In my laptop, actually, some issue is there, so I'm doing this in another laptop. Let us see there. So I will log out from this device and log in there. Just wait. Okay. Okay. There's some issue. I'll resolve it. Give me some time, but I will not waste time here. Later on, we'll discuss this CRQ. First, now we'll discuss the other two. Two tools we are supposed to discuss today. We'll discuss the other two. Anyway, the tool we are supposed to discuss here is IBM tool. Okay, there is IBM KeySkip. So it is IBM Quantum Experience. There is one interface here. So we'll go for that. Uh, oh, um, so we'll see IBM Quantum tool is supposed to use. So where KeySkip is the package based on Python that we use. For this, actually required one ID first. So those who have not used this, so you need to know that. So first you need to create one IBM ID account, IBM account, because you want to use their service. So already I have one. So its account creation is very simple. You can do it yourself. I'll use my own. So once you create an account, you'll see some page like this. They will welcome you this way. And here you notice one very important thing which is required sometimes, because in the program itself we required to interact with the quantum hardware. But at this moment we are on our own computer. So meaning is it is not the quantum one, the classical one. So when you after simulation is done in your computer, you can again port your result to the actual quantum hardware. To do that, actually, you required one, what to say, authentication. So that authentication already is given. API token, if you notice here, this API token is there. If you see this API token written there, all right, you have to copy this once it is required, all right. So this can be seen in your account profile also. If you see here, it will be there, but at this moment my profile is open. Now, two things you will see here. One is your IBM Quantum Composer, and there is your IBM Quantum Lab. All right, both can be, utilized to do the things. All right, one is very graphical, which is user friendly, and another is also the similar way, but we normally use that Composer one. All right. Now, let us see if we run with that Composer one, what will happen. Okay, suppose we want to create one new file, new program over here. So it is basically your, what to say, very interactive sort of, software. User interface is there. So you can directly drag and drop can be used, or you can write your code, right? You see here, main library is your OpenQSM. Already discussed that in last class. Discuss, no, we just mentioned what is that OpenQSM or OpenQSM 2.0 version. So here normally we'll do that, right? Now we'll start simple way. We can do that. Let us say one small example I want to just show you first. Let me write a blank presentation. Suppose we have a there are different type of gates are available over here. One is, let us say, this is a C0 gate or Feynman gate. A, B, this is A, and this is A XOR B. It will work like this. Another is inverter NOT gate. Basically, we use Pauli X gate for that. So if it is A, it will be A inverse. Lots of gates are there. So another is your, say, Toffoli gate. So Toffoli gate symbol will be like this. Right? Here it is A, this is B, this is C, this will be A, this is B, this is A, B, or C. Okay. So we know this will perform an XOR operation over here, and sometimes also you can use for copying purpose, for inviting purpose also this is possible. Anyway, this is okay. Now, in the beginning, we will simply use them and try to see. Then we'll try to design some circuit. So let us stop it for time being here. Then come back to this. Say the things I told you. These are, say, some sort of qubit created. That is Q0, Q1, Q2 sort of things. If you see, it's small little bit. That's right. And Q3, because if you see why, because if you need more lines, you can change over here. Say if this is QREG, QREG, that is quantum register Q. We have created 3, just 3-bit long. I can make it 4 if you want. Sorry, not 34, 4 suppose. I can make it 4. Similar way, since we require a measurement, I can make it 4 here. So it will be classical register. So now if you see that, we're changing to 4. 0, 1, 2, 3, that is total 4. And similarly, there will be C4, that is your classical register. So quantum register is basically the operation we want to perform over there, and classical register basically to measure. After doing the operation, we need to measure it, because at this moment we want to perform some simulation over this machine, so we need to measure it. So for that purpose, we require classical register also. So you have to include this file. you leave 1.inc, that is important. So that is by default, it's like C include stdio.h site. So you can include that. Now we are defining one register or of 4-bit length, that is quantum register. Another, and the name is Q. Another register C, this classical register of length 4. Okay. Now let us say here for our business, we make it small. Say we want to, it's a not get or proudly X get, you can say. We'll put over here. So once you place this, you will see, meaning you can do this using writing a code in Quantum Lab, or it is a drag and drop. So if you write, automatically your code will be there. You see X Q0, meaning is in Q0 qubit, that is the first line, we are putting X gate. Suppose instead of dragging and drag and drop, I'm suppose this time writing, we are putting a head mark gate in Q1 qubit. So what I'll write, head mark gate H, suppose, I'm sorry, H Q1 1. If I write over there, automatically the head mark gate is on qubit 1. You have seen. So same thing I can do using drag and drop. So I can put a gate over here like that. All right. Whether it is okay, whether it's a circuit or not, that is a different issue, because that we have not designed. We design now. So thus you can simply drag and drop. So this is your CNOT gate. You can easily put somewhere wherever you want. But you need to just place this way. This way. All right. If you want to pass to some other, then it can, or this is 2, the length, that's why the length is 2, that way. If for quantum gate we require 3, so let us make it 3. Sorry, for Toffoli we require 3, let us make it 3. So now let us say Toffoli, you can place this way you can do. All right. And suppose we want to reset the value over here, so you can reset the value. Reset the value meaning is this is your qubit 0. All right, we are resetting whatever is there. We now reset to 0. All right, if you want to make 1, then simply put 1 inverter. So this way you will place the gate depending on the design, whatever you make. And sometime if you want to join, meaning is what? Say these two are joined, meaning is whatever value is there in the Q2, that value will be at this moment, it will affect the value in Q1. All right, that is the join if you want. Other gates are like this: T gate, shift gate, Z. All right, so all gates are there. TDG gate, next your square root X gate. All right, all gates are there. Next, this is for measurement purpose. All right, measurement is all like this. Say what we want to measure or which bit we want to measure. Suppose this Q0, wait, suppose the Q0 qubit, this line, we want to measure, let us say in our classical register. So classical register are defined here as C. If you see that C, this is C. Total length is your 3. Now we will take this measurement, all right, and we'll drag from here to 3. Basically, just place over here. It will be okay. Now, similar, suppose this two, we don't want to measure Q1. Let us say Q2 we want to measure. Similar way, just place that over in. Oh, sorry. So it will automatically point to that one. So now, if you see the code, the respective code, that we also can do, because in Quantum Lab normally we write this, but Quantum Composer drag and drop. You will see here what we are doing. We are reset, okay, that register are defined. Now reset Q0, if you see I have put 0 over here. So we are initializing this to 0, initializing that Q bit to 0. So it is 0 Q bit. Next we are placing a head mark gate in where in Q bit 2. So we have seen that is 2 because first we have done this, that's why it is appearing in the beginning. Next we are, and Pauli X gate or NOT gate we are placing over in Q0 in the first and Q bit or first line, you can say. So this one, not this one. Next we are putting one C0 gate, that is CCX, control CX or CCX. So this we are putting, CX gate, control X gate. That is in Q0 and Q1. If you see, this is a control X. This is also known as C0 gate and Feynman gate. So this one. Next we are putting one Toffoli gate. This is also known as square of this gate. Right? So CCX, that is control X. Anyway, so what we are doing, we are writing Q0, Q1, Q2, meaning is 2 will be your control bit, Q0 and Q2, Q1, and Q2 will be the target bit. Right? The target bit is this there. Next, we are putting a swap gate. You are joining these two, basically swap. Swap is again the value I told you. The Q2 value is once there, it is now available over here. Similar way, once Q1 value is here, it is also available over Q2. So ultimately, bits are swapped, get swapped. So it is swap gate. It's done in between Q1 and Q2. Next, we use the measurement, one from Q0, another from Q2. You see, measure Q0 to classical register, first classical register bit, C0. Measure Q2 where the third bit of the classical register, right? This. So thus code will be generated. You can either write this code in your, in your quantum lab or in Jupyter notebook also. You can download Qiskit, import your Qiskit, all these things, and you can write this code. Then also it will work. But anyway, here we're using this one. It will be easier for us. Now let us say this way we'll do. Let us design one circuit. So how will design a circuit? A simple circuit will design. Let us say already we understand these gates. This is your NOT gate, Pauli X. This is our C0 gate, and this is our CCX. You can say this is our CX gate. This is our X gate, and this is CCX. This is also known as Toffoli gate. This is known as C0 gate, and this is Pauli X or NOT gate. So these three normally we'll try to use here. Let us say we want to perform addition. So if you want to perform addition, what is required? We require some something like this. This is for sum, right? That is required. Next, for carry purpose, we required something like C in, or in this case, we are writing this. This is C in, and you can write for AB. So these two particular equations we require to design that, suppose, adder. Next, let us say to do this, what we require. So these are A, B, C. Now our first requirement is A. So this can easily be done. So how we'll do this? If I write one Feynman gate over here, this becomes A XOR B, because if you see a Feynman gate, it will A XOR B kind. So it will be like this. First, let us take a simple way to do that. Next, if we make it happen over here, so A XOR B, and this is C, so ultimately this will be A XOR B XOR C. So this particular line will give us the sum. All right, so that will get this way. Now what we required our carry part. carry part will be A XOR B and C. Suppose XOR, let us consider AB. Now you see A XOR B and C is there. This is our A XOR B available over here, and we require C means this. Now, if you remember my first class, I told you when you want to implement this operation, actually, whatever the way we try to do, it will not help us. So for that, we required extra lines, or that is named as ancillary line. I told you in reversible computing when I discussed the first class. So when extra line is added, that is known as ancillary line. Now what will happen? If I write this, now I understand this is my sum, because this is giving us A XOR B XOR C. Alright, now I require this one. Now see how I get this. If you see this topology giving us A and AND operation, that is A and B, and XOR of C. Alright, so what we'll do here to see, try to see, if I use one topology over here, say it will be what? AB. First of all, this will be AB and XOR of something. Something means this bit. Since at this moment we required some of the things are like this, so that's why we don't need this. I mean, we just can make some variable over here. One easy way, there are lots of ways, but one easy is let us make it constant, because it's an ancillary line, make it constant. So once we make it constant, this become AB only. AB XOR this means 0, it is AB. Now we know AB. AB is there, so this AB is there. A XOR B is available over here. C is up to this moment, C is here. So these things we need to now utilize. So what we will do? This is our AB. AB will be okay, A XOR. A XOR B and C, right? So meaning is this and this if we make, and we create a topology over here, and here topology if we insert, what will happen? Just let me rub this first. Become directly. So we know this is our AB. So now I am putting topology over here. What will happen? This is your, this value is A XOR B, this value is C, all right, and this value is now what? AB. So ultimately this value will be AB, that is A XOR B C, and XOR what? This value. What is that? This value is AB. So this is giving us the carry. All right. So for full adder, this will be the circuit for us. Okay. So we can, I mean, consider this. Let us say. That's good. This is actually normally the easiest one. That's why I try to show you. For experienced people, this is nothing, but for people who are new to this particular tool, I used to see, because this adder is known to everyone, is a very simple circuit. But for quantum, I mean implementation, so how we can do that? And that is our main purpose. Just wait. So now we'll do that. So we required one. If we say their single bit, so 1, 2, 3. 3 is okay, and 4. 4, this will be 4. And for classical also we make it 4 bit. Now let us say first where is it? Now what I'll do, actually my screen is small, so it's coming properly. And then many components we need to look into. So first we will place these are our ABC we are considering ABC like that. Say we can label it. So first we will use affiliate over here. Oh, it's not new one, sorry. New one is there. This one, this is the new one. So here we are considering. So here we are placing the following. Okay. Then we required one because this is A XOR B. We required this one. And remember, we required this step to be. This must be reset to 0. This will must be reset to 0. This one. Because we want to create an LCD over there. Next is your. We'll make. Sorry. Okay. So corresponding things will changing. So the third bit we are resetting to 0. Reset Q to 0. Next we are using control gate or control CX gate. So in Q0, Q1 will be control, Q2 will be the target that way. And next we are using a control X or C0 gate on bit Q0, Q1. Then again a topoli gate between your actually we got 4 lines. So 0, 1, 2, 3, 4 line is there. 4 lines should be there. 3 is coming. It should be 4. It's 4. 4 line. And this is not here. 4 line, and this might go over here. And the here also should be here. Let me see where to first started. One is placed over here. This is placed over here. Okay. So this way. Next is another topology between this here. This. Let me from here and this. Yes, from here, and another synod gate is required right over here. Sorry, not here. It is here. Just that here. Okay. So this is our circuit. This is our circuit. So we'll resetting the last ancilia with 0, and next we are implementing one topology we have seen. Next the CNOT gate. The circuit we have shown you earlier this way. Right. Because we required that A XOR B. Okay, it is available over here. It is available over here. Next, we required AB. I will get it. AB XOR C. C is made of here as 0, so it becomes AB. Now A XOR B and C is important. So C is here. So we are again using topology out of this. So this is now acting as your this particular topology function that we know. What is that topology function? This is a topology function is like this. So that we are implementing. So this is A, B is your C, this is C, A XOR B into C, XOR B into C, and XOR C. C means wherever the target bit. Target bit is this. What is the result? Result is in this case AB. So A is coming. And this is our carry. Sum is what? Here it is A XOR B, and C is also required. So this result XOR with C. So it is A XOR B XOR C. So that part we have implemented. So now if you see, circuit becomes like this. So once you make this circuit, you see whatever we have done, everything is written over here. Now we need to take the measurement of this. Circuit is designed. It's a full ladder circuit now. We will take what we need to measure. Measurement other actually we don't need. So we don't need means they are unused, so they are garbage. Now what we need if you notice sum and carry part. Where is carry part? Carry part is in this Q3, and where is sum part? Sum part is available in Q2. So this two we require. That's why our measurement will be from Q2 and Q3 only. So from Q2 we will measure. It will make a measurement. Also we require to measure our carry part. So that's why. So measurement are basically some gates. Okay. And if you want to see the other value, we can create, no problem. So measurement function is basically some gates. Okay. Now if you want to change or see the things, you can put the value and see. So let us say we are making here some, let us say 0. Resetting this 0. And this is also suppose 0. The first resetting. Not this one here. Then let us assume we are putting one. Where is the X? No. Putting an inverter over here. Also an inverter over here. Alright. And we're measuring, and resetting is done there, and also we're putting this. Okay. So this is the circuit, and this is the measurement. Now, if you want to see where is the other thing? Another measurement. Okay. Now, if you want to see, once we are doing these things parallelly, computational basis states also coming up. If you see that, all right. And if you see your state vector output, it is approximately almost one kind. All right. So where it is one, if you see your 1, 2, 3, 4, because the length is 4. So total this much possibility. All right. So here 1, 0, 0, 1. That is your, okay, in that state your maximum probability of getting the correct result. That is the vector output. And if you want to see this the computational basis, all right. Again, you can see the burst clarifying. Things are coming small. No problem. You can visualize in this tool, right, where it is. We are not using phase gate, but still it will say in terms of phase. So things are very small. So here also you can see, because it is a visualization tool. So you can see it here. Probably you can see here if you want to see. And state vector can be seen this way, what are the state vector. Okay. So if you see only one situation, the probability is high, I mean the maximum one, and rest are not. So that's why if you just see the state vector, all are 0, 0, 0, here it is 1, 0, right? So in this stage, its probability of getting the result is high, or getting the maximum accuracy basically. So this way you can design any required circuit, and a corresponding codes will be generated over here. So this is part of quantum experience or quantum exposure, that is tool, Qiskit tool, part of quantum exposure again, that you can do. Other way, if you have Python, there also you can install Qiskit and you can import them and use almost similar kind of thing, and you can view the result or output. So that is also possible. Now let us see some other, say another circuit. Before that, another circuit we'll try, then we'll go for again something else. See how some few what to say, small application or small operation are not good in quantum, that also we'll try to see. First, let us again see one example. Say we'll try to compare bits. All right. Say comparator. Suppose if you want to see a comparator, comparator basically will compare this way. Compare this means it will be basically what, A bar B. This result is A bar B, and somewhere it is AB. It is basically A, your B bar, and somewhere it is basically what, A equal B. So A equal B can be seen this way. If we use our operation, maybe like this way, A B, because 0 0 it will be 0, 1 1 it will be 1. If I make it not, all right, then this value, sorry, 0 0 it will be 1 1, also it will be 0. So if I make it invert, so for 0 0 case it will be 1, 1 1 case it will be 1. So ultimately this will tell us the equal, bits are equal. So these conditions we basically require. One is what, A bar B, and there is A B bar, and there is A XOR this. So this suppose we want to implement. So for this again, what we'll see, let us see first. Let us do what, make this 0. This is A and this is B, because comparator required this 2 bit to compare, the basic one. So if we place this way, this become AB, because AB XOR 0 means AB, so this become AB. Now what I need, I required sorry, it will lead to something else. Okay, what I'll do, suppose I'll put a NOT gate over here. If I put a NOT gate over here, so this become basically A bar B. So this will give us A smaller than B. Okay. Next time what we need, we required, because this is not a very good circuit, but still let us do this, because we are creating lots of and serial line, but for simplicity or understanding purpose, let us do that. This is our A smaller than B. Next, let us say B is required. So all gates are required. Let me do one thing. Let me make a copy first because that is important. A and B is there. So I required is AB. Let me see how many times. So I'm putting 0 over there. So I'm making 1. So not get. Wherever I want put doesn't matter. So this value is again what? Here it is your A. Here it is your B. Okay. So now what I required. Say put an inverter over here and we'll make something like this 0. So ultimately this becomes A bar B. So that we need. Okay. And next we need is A B bar. B is there. B is also there. B bar. So we put a bar over here. There will be all right, and A is there. So A B bar. A very good circuit, but let me see again. A. So this will be your A B bar. That is okay. Next one is what? Here you can perform an inverter. So this becomes A XOR B bar. So now these are not used. We don't need them. These are all garbage. These are all garbage. We required 1, 2, 3, 4 ancilia. 4 ancilia extra lines required. We can optimize this circuit. And these are our output. This line will tell you equal or not. I mean, bit are equal or not. This line will tell you whether B is greater or not, and this line tell you whether A is smaller or not. So this circuit you can design if you want, and design this circuit. Let us see how we can design this circuit. So sorry, one more thing. Here I made one simple mistake. If you see, this is actually not A, and this is B. So this is B. All right. Here it is A. So it will be this one will be basically small mistake. No, sorry. Basically something like this. So here it is B, and this because I made it, I interchanged this. That's why that is the confusion. So anyway, it will B inverse, and this is A. So this result is A, B, this one. Okay, and this one will be what? Next one is B required. So from here, yeah, now this will be A. Because this is A actually is connected to A. Now this line is connected to A. So this is A, and we make it negative. So you know A inverse. A inverse, and this is B. This is that's the rotation. So so let us see this. So we'll let us save it. There is another file. So here we required 1, 2, 6 bit. Total 6 required. So first bit will be your again. So it. You can write over here Cx from Q0 to Q2. Okay, so this you can write over here. So this is not required. This is not required. Next, we required second one to that 0, 1, 2, 3. Next we require will be like this: Cx Q1 Q3. So that it is coming over here. If you see, coming over here, if you see, okay? And we need to initialize this to be 0. This must be 0. That is a reset. Reset Q2. Also, you need to reset Q3. Reset. So once that is done, next is basically what we need. If you notice here, you see in circuit over here. Next, I require that B and A is coming over here. I require an inverter over there. Then one, so I required one inverter where I required an inverter on this one Q2. Q2. If I make an inverter over here, it should become A bar and B. A bar is coming. So once A bar is coming over here in Q2, so I can make like this way. CCX Q Q bar, that is, so it will be your Q2, I think. Q2, comma, B is in your B in, that can be done. B is in your Q1, A bar is in your Q2. Q1, Q1, and target is your, what is the target? Q4, Q4. It is basically that. So you see, this will be your A bar, where I'm copying A bar because this is 0, A bar, and this is B. So A B bar, right? And target is your, what is the target? Target is Q4. For that, I need to mislead this 0 again. Q4, I'll place 0. All right. So next, what is required? A bar B is coming. A B bar. So A B bar is coming. So next, I required B bar. Where is it? B is B bar is there. This is this Q3. So Q3 is here. So I required an inverter over here. Q3. So what I require, X Q3. I require the inverter. The first one is your what your I require a CCX bit now. CCX. What is your Q0? Okay, and B bar is at Q3. So Q3, and result will be in Q5. Okay, Q5. All right. So that is the result. Okay, next again, this must be again in select to 0. So we set the effect to 0. So this is done. Now we require that AB bar must be this one, for equal region. So that is your basically CX Q0 comma Q1. So putting that one, and it is A XOR B. Now it must be again inverted. If you see, then only you will get A XOR B, and it must be inverted. Q again. So for inversion purpose, what will do? X Q1. Right. So that is. Now, if you see the circuit, you can save the circuit. Remember, all the circuits you design can be saved. Okay. What is done? It is a comparator circuit now. Something is problem. My computer is having some problem. Anyway, becoming slow, I think. Anyway, so I'm making it now a comparator circuit. What happened? So first, Q0 is A suppose, and Q1 is B suppose. So A, B, I'm using C naught gate. So A XOR B and inverter. So it is in this particular line, Q1 line will now give us A equal B. Next, Q2 line will give us what? Not Q2 line. That's Q3 line. Q3 line will give us. Let me see. So the circuit. Q3 line. Oh, happy birthday. Q3 line. Let me see. It's become very small. And so many problems. Let us save this circuit. Just wait, I have downloaded this. So let us see this circuit what I have done. So this is the circuit I draw there. So you can download the thing. So now if you notice this circuit, what happened? So this is my A. Sorry, I can't write. Now if you see here, okay. So suppose this is my A, this is my B. Okay. Since I reset this to 0, so again this become our A and this become our B. So I'm resetting this to 0. This is our B. And I'm putting an inverter, meaning this become A invert. Now this is B, this is A inverse, and this is now 0. So this become A. Okay. And what is done next? This is our B. This B is inverted over here. All right. And if you notice this A is intact. So A and B invert, and this is zeros. That's why this become this. And this A and B are intact. I am putting one C X gate, control X gate. So this the meaning is A XOR B. But I am writing one inverter, so this becomes A XOR B invert. So meaning is this is one output line for us, which will give us A smaller than B. This is another output line which will give us A greater than B, and this will give us A equal to, so not this one, this will give us this line A equal to B. A equal to what happened? A equal B. A equal B. Alright, so this is circuit you can download and you can use if you want. Alright, and this is not complete because we have not performed the measurement. So measurement is required for which bit you need to see. First one is Q1 is required for measurement purpose. This will be equal. Next requirement will be this one Q4 and Q5. So Q4, Q5 and Q1 are required for measurement. So we need to perform that measurement. So how that measurement is done, let us see. Where is that? This. So measurement is from this. So like this way. C1 or whoever you want to perform measurement should not be. Measurement on again. Let me see. Okay, one is your one, another is your one. One is done. Next one is your where is it? Measure 6. There one is Q4 and she says Q4. One is Q4. So meaning is Q4 to some register. Any register you can take. This one Q4 if I want. Next another measurement and that Q5 that need to be measured. So C5 classical register, right? So you can see, okay. So this measurement, now the circuit will be like this. You can see the state vector if you want and save it. So these things you can again open in quantum lab. They also can write this code. And the circuit can be again, if we download it again, as PDF also you can download or as PNG also you can download. Suppose I am downloading now again. If you see the circuit, these are the measurement. Oh, this is a mistake. This must be later. Not an issue, but normally we put the measurement later, not in the beginning. So let us copy this measurement, not here, because again this may create some error. Measurement must be at the last. Okay. So now let us see. If you see, the measurement must be like this. So here, if you notice, here we got A equal to B. So we measured this between classical register, and here we are getting Uh, this is beaver. So A beaver and this A. So that's why uh, this. Sorry, here we are getting this. So these 3 bits are actually major. Rest actually unused, so they will be garbage. Okay, you can see the state vectors and other things is one available there. Now there is one question. At this moment, they are having actually less number of qubit. So using less than 6 qubits, we need to adjust the circuit. We need to either optimize or do in a different way because we are using 6 qubit over here, right? So that can be done. So if you want to make it more, then you need to look into what other possible servers are there. So that let me see whether this I can see here or not. Server is not running, maybe that's why. So if I want to run the server, then we'll see lots of servers are available. Some servers will run for 6 bits, some for maybe 26 bits. So then we need to select that particular server. So at this moment, we are actually unable to run that because our qubit is a little bit longer, 6 bits. Perhaps it is working on 4 quantum bit thing, that's right. That's can. Mm-hmm. I need to again log in. So now I'll again need to log in. So those having account, you can see, you can check one. So another, this way you can handle the things. The other tool I want to show you if you want. Give me just few. Okay, let us see the other tool. One more thing I wanted to show, but you know, time is up there. So this is basically your Jupyter or Jupyter, whatever you say. So that you download, and you need to install first that this one Google CRQ. Once you install the CRQ, then you'll be able to run your programs. So let us see how we can do this. So first you need to do write something like this. I have already installed it. Once you install, you can do that. So next, suppose I will do some small things like this. Um, yes, before using, you need to read the manuals because you need to know what are the symbols. The symbols are important. So here again, almost similar. Say if you want to use X gate or that probably X gate or not gate, it will be capital X. The part of CRQ package, so you have to, I mean, you need to know first that. Next, what are the other things? Means all the other important symbols that you're supposed to use, you need to know. So let us say this is one small one. I'm making, let us say, operation. Mm, I'll not write this one. Not this one. Let's say something else I'll write. Let us say Q0 I'm writing. CIR2 dot X. I'm not writing a program. I'm simply writing some small things so that later on you can use yourself. Right? I'll not write big things out of this. Only use some small sort of symbols. So it will take time, or if error is there, it will be very, very complicated. Some problem. Let us see those problems. Last class, actually, I gave you something about this Q0. So, circuit normally handle the qubit in three different ways. I told you, can remember. One is name qubit, grid qubit, and line qubit. So that you need to use. Suppose if I use name qubit, I'm labeling it. Let us say it's on label. Okay. Another one. This CIQ. CIQ dot name qubit AB. I'm writing this. and say if you want more, then you can write more. So say 3 which I have created, very easy to create. Then we'll try to do some simple operation. Let us see. If we suppose what to happen. I'm writing this. Okay. Then I'm writing print. I'm writing this. Already it's run. Okay, it's run. It's blank. So if you remember in the last class, I told you initially there is a framework or frame. So you need to basically once you design a circuit, you need to append it, right? So then only that will be easier for you to do. Okay. So now here, if you see, let us say we do something like this. So so grid kind of things let us do. Good, I think. If we do, say, yeah. Sorry. Sorry. I have to dot grid suppose right, one function definition, right? Mm, so Pauli gets square root of Pauli. Hmm. Okay, so this is a simple function to create one circuit with two qubits, Q0, Q1. And here if you see, we are creating a grid. Grid is ultimately it's a two line. So Q0, Q1 may be there, and we are using one root x gate, that is square root x over there. And in Q0 bit we are using this x square root x, and Q1 also we are using that. And then the control z bit is between Q0 and Q1 for that line. And again, independently after using control z, again we are using square root. This is your x gate, square root x gate on Q0 and Q1. Then in that function, if circuit is true, right, if circuit exists, what we will do? It will again perform the measurement on Q0, level is Q0, and perform measurement Q1, where level is also Q1. You can write different name, but that is the level. Then we create, during the construct of class circuit, we create the blank or basic circuit, and we append our circuit we have defined here BCK3. That circuit we are defining over here, and then we will try to clean the circuit. So actually maybe that one module is not installed, that's why it is not. You see.